term, he specialized in near-infrared lanthanide luminescence, as well as the use of X-ray absorption spectroscopy to study the coordination chemistry of lanthanide complexes. He made plenty of postdoctoral stay at the European synchrotron radiation facility. And finally, in 2008, he obtained a permanent position at the Inorganic and Physical Chemistry Department of Ghent University, where he created the Luminiscent Lanthanide Lab, where his research on 4F element focused on the development of lanthanide containing luminescent materials for many applications, such as solid-state emissions, sensor, mainly focused on coordination compounds, and even MOF. The present talk is about taking advantage of lanthanide luminescence in functional MOF materials. Ahora en español, el profesor Rick Van Deun pertenece a la Universidad de Ghent. Se recibió de químico en la Universidad de Leuven en Bélgica, con la supervisión del profesor Cohen Binemans y la doctora Christian Gorler-Worm, básicamente centrado en compuestos de lantánidos con emisiones en la zona del visible del infrarrojo cercano. Su grupo actualmente está enfocado en estudiar MOF y compuestos de coordinación basados en lantanio con diferentes propósitos. So, this is your turn, Rick, in order to start with your presentation. So we welcome to ArMOF. This is the first edition, so it would be nice to hear your presentation.
Okay, thank you very much, Germán. Can you see my presentation?
Yes.
Okay,
I can see
okay. Okay, so first, of course, I would like to thank the organizers for this really nice opportunity to share some results that we obtained on luminescent lanthanide materials, more or less MOFs or more general coordination polymers. So my outline will start with introduction to lanthanides and their luminescence, just briefly introducing them and a few of the most important features. Then, of course, I will try to convince you why we are interested in lanthanide functionalized MOFs. And then I will share 4 different results with you. So the first one is our first attempt. It's already more than 10 years ago. On
I can
a European terephthalate MOF. Can you not hear me?
Yes. It's okay now.
Okay. So I will show 4 sets of results. The first of which is a terephthalate European MOF. The second one is on a MOF which has been synthesized with mechanochemistry. Then I will show you results on a post-functionalized MOF. And finally, some results on a coordination polymer that is able to emit near-infrared emission. And of course, then I will conclude. So why lanthanides, or what are the lanthanides? Well, I think most of us know that they are usually pushed down to the bottom of the periodic table. But if we were to show the periodic table as we should show it, then of course they should be here, the 4F and 5F elements between the S and the D block. So the lanthanide series goes for element 57 to element 71. And they got their name from the Greek lanthanein, which means to lie hidden. And this already points to the fact that the discovery or the stories with respect to the discovery of these elements were not very straightforward. They were not very easy to obtain in a pure form. And this is mostly due to the fact that they have rather similar chemical properties. And so it's non-trivial to separate them, to obtain them in a pure form. And a second, well, I would say disadvantage is that they do not occur in highly concentrated deposits, but they are more dispersed in nature.
Sorry, Rick.
Yeah.
Can you put the complete screen, please?
Yeah.
As a presentation.
Yeah, the problem is if I use my complete screen, then I cannot point anymore. So I cannot point at anything. Oh yeah, maybe. Okay. Ooh.
I can see the arrow there. Yeah.
Yeah, now I can see it. Yeah, okay.
It's
I
better.
didn't know that. Yeah. Okay, thank you.
Thank you.
Yeah, so of course the most important features of the lanthanide series is actually a gradual filling of the 4F shell. And this is quite obvious when you look at this table, which contains all the lanthanides. In addition, also yttrium. Yttrium is not a lanthanide, but it's a rare earth element, and it shares some properties with the lanthanides. That's why it's often considered together. When you look at the trivalent positive oxidation state of the lanthanides, then you see indeed that we have a really gradual filling of the 4F orbitals from 0 electrons at lanthanum to 14 electrons at lutetium. Maybe even more important is the fact that the 4F orbitals are called inward or inner orbitals, because the 4F orbitals are more or less shielded from the outside by filled 5s and 5p orbitals. So here, this is a scheme that shows in a rather descriptive way what the likelihood is to encounter an electron when you start here from the nucleus of the lanthanide and you go outwards. And then you see indeed that you first have this 4F shell, and then more outward you have 5s and 5p. So yeah, this is already said. Of course, because the 4F electrons are then, let's say, hidden inside the electron cloud, and the 4F orbitals are also rather inner orbitals, they cannot really overlap with other orbitals from ligands outside. So this means that you don't have any covalency, or hardly any covalency. So the coordination chemistry and the bonding of lanthanides is largely ionic and based on electrostatic repulsion and attraction, of course. And also another effect is that the crystal field, of course, doesn't have a lot of influence on the spectroscopic properties. An important scheme for anyone who studies lanthanide luminescence or the spectroscopy of lanthanides is a decay diagram shown here. So this is basically a collection of electronic states, energy levels of most of the lanthanides. And this is quite important to explain which kind of transitions can occur in lanthanide materials, both in an absorption way, so from the ground state to a higher excited state, but also in luminescence, where you have a excited state decaying to a lower lying state or more lower lying states. So the electronic transitions within the valence shell are, of course, 4F transitions. And the problem is that you keep the same parity, and then Laporte says, well, you cannot have that transition is forbidden because of the selection rules. So in principle, we should not see any transition there, but nevertheless, there is a small relaxation effect. And so you can observe, of course, 4F transitions of lanthanides, but nevertheless, they are always weak. Yeah? So in absorption, you typically have molar absorptivity coefficients that are less than 10, but even sometimes less than 1 liter per mole per centimeter. And that means that it's difficult to excite a lanthanide. I mean, by directly exciting into the 4F levels. Of course, luminescence is the other way around. So there you start from an excited electronic state, and you see a decay to lower lying states. And I have here cut out a very small piece of the decay diagram, of the energy level diagram of trivalent europium. And this is a typical emission spectrum of trivalent europium. You see immediately that the bands are really narrow. That's also an effect of the shielded nature of the 4F orbitals. And if I now push my button, then you will see that from this level, the 5D0 level, you will see some transitions occurring to some of these lower lying levels. And also here you will see that the corresponding peak in the spectrum will be highlighted. So I'll do that. So now you see all the peaks appearing. And so there is 5 transitions in this case. Of course, in principle, you can go to further, to longer wavelengths, but at that moment, we didn't have the equipment to do that. So luminescence is the transition typically from an excited electronic state to a lower lying state. But of course, these are also 4F transitions, so they should also be forbidden. But of course, if you don't have, if the excited state doesn't have any alternative way of relaxing to the ground state or to a lower lying state, then we will nevertheless see emission. But of course, if you want to get an excited state populated, you have to excite it. And the excitation is typically an absorption phenomenon, which is also forbidden. So luckily, you can circumvent that. There's one way to excite directly in the 4F transitions by using a very high power excitation source, such as a laser. Then you can, of course, also, well, nevertheless, get some energy in there, but that's a little bit awkward and expensive. So there is a second way to circumvent that, and that is by making, for example, coordination compounds where you have organic ligands coordinating to the lanthanides, and these are then harvesting energy because the absorption transitions in these organic compounds are allowed, and so they are much more intense. So this is a scheme where the little sphere here is a lanthanide, trivalent lanthanide, and this half circle is a ligand. And so the ligand contains an organic moiety, an organic group, for instance, a chromophore, and this chromophore can absorb a lot of energy, a lot of light here. Then if you have selected your ligand and your chromophore properly, then the excited antenna can then, give on the energy to the lanthanide, which will then emit it at its specific wavelengths. And of course, for obvious reasons, this is called the antenna effect. And that is also what we try to obtain in the materials that I will show you. So why would we be interested in lanthanide functionalized MOFs? Well, first of all, of course, what is a MOF? I assume that in this workshop, that's not really something I have to explain. So metal organic frameworks are obviously combinations of metal ions with linking molecules that can lead to three-dimensional porous networks. And of course, they're quite flexible. I mean, not only can the MOF be flexible literally, but you also have a lot of flexibility to design and to create MOFs, because of course you have almost the entire periodic system of elements, which are mostly metals. And of course, the ideas that you can have to develop linkers is also endless in principle. So they have been studied, for instance, for applications in catalysis, gas separation, gas storage sensing, etc. And of course, if you can combine luminescence with MOFs, and you can make a material that is very specific in its emission, for instance, it can change the emission color as a function of temperature or as a function of excitation wavelength, then you can make something that is really very hard to mimic, and then this could have potential as anti-counterfeiting materials. So basically, there is two large ways to obtain a lanthanide MOF. The first one, maybe the most obvious one, is using the lanthanide as the node. So the lanthanide is really the core element that builds up the structure. Sometimes this is not very easy, because contrary to transition metal ions, which have, let's say, predetermined bond symmetries because of the hybridization of the valence orbitals, I mean, it's always octahedral or tetrahedral or square planar. You don't have that with lanthanides. The lanthanides do not have a predetermined coordination symmetry because of the electrostatic nature. So yeah, this is much harder to predict what kind of a MOF you will end up with. So that is one way to do this. Another way is use a existing MOF that is, for instance, built up from aluminium ions, but then having a functionality that you can use to post-modify this MOF by introducing lanthanides in a second stage. That's another way of obtaining MOFs that are really containing functional and luminescent lanthanides. Yeah, this is just an example of a well-known zinc MOF. So you have here terephthalic acid or terephthalate, and you end up here with a porous material. Of course, other examples exist, in this case, copper and a tricarboxylic acid, that you end up with some different MOF. In this case, or in both cases, obviously, they're porous, but it's not always the case. If you then have a well-defined MOF, then of course you can play with for instance, the linker length. In what's called isoreticular synthesis, you can vary the pore size basically by changing the linker and varying the length of the linker. That's something you can do. So the first set of results that I would like to show you is a terephthalate europium MOF. So this was the first steps that we made in lanthanide MOFs. We hadn't done anything before, and it was the first PhD student that entered my group who, well, got the assignment of looking into literature, and so he found a rather simple synthetic procedure to make lanthanide MOFs. But in that paper, the MOFs were actually based on heavy lanthanide elements, which means that the elements came from the second half of the lanthanide series. So they have smaller ionic radius, but they are heavier. Quite common linker, also terephthalate was used. It's a mild synthesis, so it's not an autoclave synthesis, but just a open beaker on the air with moderate temperature. And indeed, he obtained a three-dimensional network, but he used light lanthanides. So he used lanthanides from the first half. And what he found is that the crystal structure that he could determine from the europium MOF, and the other three are isomorphous, was different than the reported crystal structures from the MOFs that were made in a similar way. But the only difference was that in the literature, there was heavy lanthanides, whereas we used the light ones. There's also a subtlety, well, it's not really a subtlety, but the fact that you can debate whether this is a MOF or not, because you can distinguish pores. These are some coordination environments, but here you can distinguish pores if you want to, but the problem is that the pores are actually filled with coordinating solvent molecules, in this case DMF and water. And of course, you could in theory remove these, but then you also alter the coordination of the europium nodes, and then most likely the MOF would collapse. So it's not porous, but nevertheless, it showed some really nice luminescence. So the four lanthanide ions here showed good luminescence. The blue part of the spectrum is typically the excitation spectrum, and the red part is the emission spectrum. So you see also from looking at the excitation spectra that you see a lot of narrow peaks. So this means that you have direct excitation of the lanthanide through the 4F transitions, but you also have at shorter wavelength a broad band, and the broad band stems from the terephthalic acid or the terephthalate, which is the antenna, the ligand. So it can also be efficiently excited through the terephthalate, but it's not the best linker, because you see that the intensity of the 4F peaks is more or less the same as the intensity of the broadband. So that indicates that it's not really that efficient. But nevertheless, that was the first attempt that we made. And probably the linker is not ideal, because for most of the lanthanides, the distance between the triplet level and the accepting levels is too large. For praseodymium, there's an exception, but here this level is actually too close, so there you get back transfer. And this is just a table of contents graphic where you have a small vial with some of the europium MOF under UV light, and you see quite clearly the nice red luminescence. So this was published in Inorganic Chemistry. It was the work of Roel de Cat and the first PhD student in 2012. Then a second set of results deals with mechanochemical synthesis. And here another student tried to synthesize coordination polymers based on the ligand that is shown here, so 2,3-pyrazine dicarboxylic acid. And he used different procedures. He used a literature synthesis, which, well, was classic in the sense that it was a wet synthesis, so you use a solvent and reflux conditions. And he then tried to obtain the same materials via mechanochemical synthesis. So this means that you have the powdered reagents and you grind them really finely, really intimately in a mortar. And in that way, sometimes adding a really small amount of solvent has also to be done. But in that way, you make the reagents react with one another, and you also can get coordination polymers in that way. So we made two distinct coordination polymers, the one based on lanthanum as the nodes, and the other was based on cerium. And then he doped these with 4 visible emitting lanthanides. I mean, doping this means, of course, that a small percentage of the lanthanide reagent is not lanthanum, but one of the others, and then you have a small percentage of the visible emitting lanthanide, and then you can investigate these MOFs from the point of view of the luminescence. It basically obtains two-dimensional layers that are nevertheless interconnected by hydrogen bonds, so you have a three-dimensional material. The stoichiometry is, of course, rather well, not very well. It was clear, but it's not very easy. But anyway, so we also varied the doping percentage a little bit to investigate the optimal doping percentage. I mean, optimal meaning giving the most intense luminescence, because of course you cannot keep on adding visible emitting lanthanides to increase the luminescence. When you reach a certain optimum, then the emission goes down again, and this is usually due to coordination quenching. And here, this is a infrared or a set of infrared spectra where you compare the infrared spectrum of the conventional synthesis, so the cerium coordination polymer that was used in conventional ways or made in conventional ways, and then the chemically synthesized coordination polymer also doped with the visible emitting lanthanides, and you see that the traces are quite similar. Also in powder X-ray diffraction, also the diffractograms are all very similar, and they also correspond really well to the simulated pattern. So coordination environment is not that important, but you see that you have ligands that only bind through one of the carboxylate oxygens, and there's also ligands that also bind to a carboxylate oxygen, but also through one of the nitrogens of the ring here. It's also occurring. These are two-dimensional sheets, basically looked upon from a top view. If you would tilt these 90 degrees, then you see that you have here a sheet. You have a sheet here in the middle, and you have a sheet here at the bottom, and they are interconnected via hydrogen bonds. So that is creating a three-dimensional network. They showed also really nice luminescence. Here you have quite clearly a antenna effect because you have no 4F peaks in the excitation spectra. So the broadband really means that you excite through the antenna. So the ligand absorbs light and transfers it to the lanthanide. This is the europium spectrum, terbium, dysprosium, samarium, and these behave quite nicely. This is a picture under UV light of 4 of these materials, and you see, of course, europium and terbium always are the brightest. But you see that in terbium, you could say maybe the 10% is the brightest, and for europium, it's definitely the 7.5, because relatively speaking, dysprosium and samarium are not as bright; they're hardly visible, but that's probably due to otherwise these would be overexposed, let's say. Okay, so this was something that was done by Parvis in 2016, Christenkom paper that came out of it. The third set of results is based on a known MOF, which is then post-functionalized by lanthanide complexes. And so this MOF2021 is an aluminium MOF. I will show it in the next slide how it looks. And then this was post-modified. And careful selection of the lanthanide doping, also which different lanthanides to combine in the same material, also the doping percentages, and also the beta diketone ligands would allow, and did allow, to obtain materials that show luminescence color changes based on temperature, but also wavelength variation. So these were materials that have very specific properties that are really, of course, very difficult to mimic if you don't know what it is. And that's why, we claim that it could be used for anti-counterfeiting, but of course, this is all. I mean, we are a fundamental science group, so the applications are not really the most important thing we think about at first, and maybe in a later stage we do. But okay, so this MOF2021 has aluminium nodes. These are the orange polyhedra, and they are linked by pyridine dicarboxylate linkers. And this is interesting because this 2,2' bipyridine basically also allows coordination to metal ions, and especially lanthanide ions. They like to be coordinated by this 2,2' bipyridine. And these bipyridine sites, so they can coordinate to lanthanide beta ketone complex. So I given here a small part of the backbone of the MOF. So here's the bipyridine linker, and here is a lanthanide acetylacetone beta ketone complex. So if you post-modify, I mean, you first make them off, and then you treat it with a solution of the beta ketone complex, and then the beta ketone complexes with the bipyridine linker, and then you have also a material that contains luminescent lanthanides, but they are not part of the node of the backbone of the MOF, but they are nevertheless inside and they are bound to it. In this case, you see that, yeah, it's a bit much in one picture, but you see that here in A, depending on the wavelength, you can quite clearly obtain a very different emission color. Here it's like yellow and green, but here is red and green. And then to the right, there you can see that changing the temperature, for instance here, also changes the emission color, whereas in this complex, it didn't do that because the excitation wavelength was also different. Yeah, here's a little bit explained. It's not that important, but mainly the change in color, especially with the change of temperature, is due to the fact that these energy levels, they can vary very slightly in energy by varying the temperature, and that can lead to a different energy transfer process that takes place, and that then of course can lead to a different color, a different emission color. So here you see the emission here in the this is a part of this CIE diagram where you can see that you have emission color changing from yellow at room temperature to green at the low temperature. No height, I cannot see it. Yeah, it's 280 Kelvin. Yeah, indeed. Okay. Where am I? Oh, yeah, here. Yeah, this was the work of Anna Kaczmarek, mainly 2017. We were quite happy to get it published in Advanced Functional Materials, and we also were quite happy to be able to provide the front cover picture. We called it chameleon MOFs because they behave differently when you have different circumstances. And then finally, I will also show you a small set of results based on a coordination polymer that contains near-infrared emitting lanthanides. So near-infrared or NIR, why are we interested in that? Well, first of all, let's say near-infrared emission is luminescence in a wavelength range typically between 800 and maybe 1600 nanometers. This is a wavelength range in which there are a few windows that are called telecommunication windows, in which silica is actually transparent for emission in those wavelengths. And so also in bioimaging, I mean the human tissue or the tissue also of living animals is more transparent for near-infrared emission than for visible emission. So yeah, that's why this is quite an important feature. There are many, well, quite a good number of lanthanide ions that can emit in the near-infrared, but there's 3 of them that usually are studied because there the emission is the brightest. It's neodymium, ytterbium, and erbium. But of course, the emission here being of a longer wavelength also means that the energy gap between the excited state and the accepting state is much smaller than in visible emitting lanthanides. And that means that this gap can be more easily bridged by, for instance, overtones of vibrational modes of CH, OH, or NH. So if you want to make a coordination compound, it's of course not easy to make an organic material that cannot contain CH bonds or OH or NH. But it is a fact that it's mainly in the close vicinity to the lanthanide that these groups are rather detrimental. If they're further out, then it's not that much of a problem. So, of course, making a coordination polymer also allows to make heterometallic assemblies. So you can basically make a single material that contains 2 different lanthanides as nodes, nevertheless. In this way, or in this study, this was the ligand that was used. It has a really awful name, 2-chloro-5-cyano-3,6-dihydroxybenzoquinone. It's this animal. It's also abbreviated here, but you see that you basically have a ring, and on both sides you can imagine, if you deprotonate that you have a chelate system here with 2 oxygens, and also here you have a chelate system with 2 oxygens. So you can bind, or you can bridge lanthanide nodes by coordinating them on either way of this ligand. And because this is a rather small ligand, this means that the distance between the 2 ions is actually quite small. So for instance, if you have an ytterbium here and an erbium there, then they are so close together that they can communicate with one another. And of course, communicate, I mean, there can be energy transfer from ytterbium to erbium, for instance. There were 4 compounds made. The gadolinium one is not that important, but the other 3 are important. So there is one compound that contained only ytterbium. Then there was another one that contained only erbium, and then there was a mixed compound that contained both ytterbium and erbium more or less in the same quantities. Coordination environment is not that important. I mean, it's obviously that it's also porous. The cyano groups, they are not displayed very properly because they were, what do you call that? Twinned? No, it's not twinned. But yeah, they occurred at different positions in the crystal structure. Why are people looking at ytterbium in combination with erbium? Well, erbium, I already mentioned, has a luminescence in a telecommunication window at 1.5 microns, so 1,500 and something nanometers. That's this transition. The problem is, if you want to excite erbium, for instance, in a higher level here, it's not efficient because erbium has really a poor absorption at that wavelength, 980 nanometers. Now, ytterbium only has one excited state, this one, and this state is actually quite resonant with this erbium state. And the advantage of ytterbium is that this absorption, in the absorption transition, is actually, it has a larger cross-section for absorption. So there is more light that can be absorbed. Of course, it's still not spectacular, it's still a lanthanide, but it's better than the absorption of erbium in that wavelength range. So that's why typically people use ytterbium, because it can absorb more light, and then some of this energy is then transferred to the erbium, because these levels are quite resonant, and then via relaxation to this level you get this 1.5 micron emission. In this case, this is a typical scheme for antenna effect, where you have the ligand states here, ground state singlet, and excited singlet state, and then the triplet state, and then usually that is the sequence that is followed when you want to see the emission. This ligand is rather peculiar in the sense that it has a really broad absorption band. So this is diffuse reflectance. This is an excitation spectrum, but you see it's quite similar. And it covers, basically the entire visible spectrum. So you can really select your excitation wavelength over a really broad wavelength range, sorry. This is an emission spectrum. As you see, we are here in the near infrared region. Compound 1 is the purple trace here. This is the trace of the compound that was only containing ytterbium. And you see that this has been dramatically reduced in intensity. It's only 3% of the actual intensity. Otherwise, it would be impossible to compare the intensities. But you see that in principle, the emission of ytterbium in this case is really intense. The blue curve, you see, only has a peak here. The blue curve belongs to compound 3, which only contained erbium, 100%. So you see, indeed, you have erbium emission there. And then compound 2, which is the red trace. This is the mixed compound where you have ytterbium and erbium. But you see that the ytterbium emission is much lower. I remember that this is actually only 3% of the real intensity, so it's much lower. And nevertheless, you also have a good intensity in erbium emission. And this is also something that you can study using time-resolved spectroscopy, where you use a pulsed light source and then you excite at each pulse, and you look at the intensity decay. And so the decay dynamics can tell you something about the energy transfer processes that are going on there. And so in the left pane here, you have compound 1, which is purple. But this is the coordination polymer that only contains ytterbium, 100%. So it has a rather long decay time. And then the red signal is actually the ytterbium emission in the mixed compound, so in compound number 2. And you see that this decay is much steeper, which means that the decay time is much shorter. And that is a typical phenomenon that points to the fact that this ytterbium is actually an intermediate level that is used to transfer energy to erbium. And the erbium emission is basically the same, more or less, in the two systems. So this points to the fact that indeed there is a enhancement of the erbium emission by energy transfer from ytterbium. They also have unusually long luminescence decay times. I mean, it doesn't maybe say much, but these decay times in erbium, they're typically 1 microsecond, maybe 2 microseconds. So it's here 5-fold. Also in ytterbium, this is also much longer than normal. And this is mainly due to the fact that this ligand does not have any CH or OH or NH in close vicinity of the lanthanide. So therefore you have really a low quenching degree, and that really leads to a very bright, if you can say that, near-infrared emission.
Sorry, you have 2 minutes more, right?
Yes, I'm more or less finished. Yeah. Okay. So this was published in 2019. It was the work of Flavia Artizou. So I can conclude. I think it's fair to say that we have a large variety of functional luminescent lanthanide materials, both coordination polymers and MOFs. In the first example, I showed that the lanthanide radius can really influence the crystal structure that you obtain. The second example, I showed that in some cases, the mechanochemistry can be a viable alternative to the typical or classical solvent reaction methods. In a third example, I showed you that you cannot actually use a aluminium MOF that is then post-modified by lanthanides. And the fourth example showed the near-infrared emissive materials that I just showed. Some acknowledgements, former PhD students, Roel Jing, Dimitri Parvis, fellow friends and colleagues, Flavia, Anna, Christoph, all the L3 members, and of course some funding agencies. And before I really end, I would like to highlight and celebrate the Belgian-Argentinian MOF cooperation that was established by German and Griselda, and which also already yield quite some nice results. So hereby, I really thank you very much, and I conclude my presentation. Thank you very much.
Thank you very much, Rick, for your presentation. It was brilliant, and your talk is an example of the use of lanthanide in MOF systems. And I personally, I can learn a lot about your paper. So it is nice to listen you in this ArMOF conference.
Thank you.
We have a couple of questions and comments. Mm-hmm. Firstly, we have the question of here from Griselda. Griselda said, thank you very much, Rick, for your interesting presentation. I have 2 questions referring to the incorporation of lanthanide in the form of complex in MOF2021 is very interesting. Is the synthesis very complicated? Do they do it by the thermal methods? This is the first question.
Yeah, that's of course good. Yeah, sorry. Yes, let me see. So it's this basically what we're talking about. That's a good question. Of course, when you have a PhD student doing the experiments, and it's not always easy to remember how they went. But I think the MOF2021 is a well-established synthesis route. I think you can even buy it. I'm not completely 100% sure. But then the incorporation of the lanthanide complex is typically done, if I remember correctly, by dissolving the complexes in a solvent. For instance, I think they dissolve in chloroform, but I'm not exactly sure. The MOF probably does not dissolve, but you can make a suspension of it, and then refluxing these two together for some time. It can take a few hours. Will make the lanthanide complexes go into the pores and to the linkers to coordinate. This is usually how it's done. And then afterwards, of course, it's cooled down, it's filtered off, and then the powder, the remaining powder is then washed to make sure that the complexes are not just on the surface of the MOF, but they're really in the pores. So that is more or less how it's done.
Okay.
So I don't think it's really difficult. Yeah.
No, the hydrothermal is a typical route of synthesis.
Indeed.
Okay, another question from Griselda is, finally, how do you evaluate the advantage of using MOF over other traditional luminescent materials such as oxides and salts? Yes.
Yeah, of course, the flexibility in combining different lanthanides together is actually one of the big advantages of MOFs, that you can really have a structure where you have different lanthanides that can communicate, as I showed in the near-infrared example. Yeah, typically completely inorganic materials, that is more, how should I say, it's less orderly. Yeah? There is just a bulk material, and of course the inorganic materials, they don't offer a lot of flexibility with regard to processing afterwards. If you have the luck that your MOF is slightly soluble, you can often process it better, like for instance have a drop cast film or something similar. So that is, I mean, I think in my head the most important advantage.
Yes, agree. Yes. I have another question for Agustin Godoy, who is a PhD student in our group. He's working with up conversion properties. He said, first of all, thank you for your presentation, Rick. We have seen that gadolinium enhances the emission intensity of solid doped with yttrium and erbium. What is the role of gadolinium ions in the upconversion energy transfer process, taking into account that it excited level 6? This is more specific, yes, but okay, we can go to the first question. Yeah, what is the role of gadolinium in the upconversion energy transfer process?
In upconversion, I'm not actually that certain. Well, we have seen, and we have also published the influence of gadolinium in enhancement of visible emission. Of course, that's not, I mean, visible downshifting, just downshifting, so excitation in the UV and then emission in the visible. And there, I think it is mainly due to the fact that gadolinium has some transitions in the UV. I think we know that. And the absorption cross-section of the transitions in the UV are larger than most of the transitions in the same area, but then in the other lanthanides. So I think by introducing gadolinium, you can get more energy into the system, because gadolinium really is rather efficient at absorbing the UV energy as well. Of course, in upconversion is the other way around, and we have also seen that not only gadolinium, but also lanthanum and lutetium can enhance sometimes the luminescence, but there it is often a dilution effect.
A dilution.
Yeah, a dilution, because you have maybe a doping system that is a little bit too high for optimum emission intensity, and then if you then change it, or you don't really change them, but if you then have a system where there is also a small percentage of gadolinium, then you have a dilution, and you are a bit further from this concentration quenching, and that can be also the reason that you have a increased intensity. But I think there is certainly more work to really investigate this in detail with advanced spectroscopy measures, I think, because it's, yeah, I mean, it's an effect that I think is recognized, but it's not always very obvious what the reason is.
Yes.
Yeah.
Okay. Yes, this is a supposition, because gadolinium can act as decrease the concentration quenching in lanthanum systems, right?
Yeah.
Okay, and we have the last question from Matthias. He said, we have seen that some synthesis procedure for rare earth BTC MOF in the literature, which report porosity as measured via nitrogen adsorption. Do you know about a process for activation that would not result in collapse of the framework?
You mean by removing the solvent molecules that are actually coordinating. I think,
yes, related with that. Yeah.
No, in that way, I don't really know any alternative, because I mean, what can you do to make it porous? It's remove the molecules and then it will collapse probably. So I think you really have to build a completely different MOF in which, in some way you have to take into account, of course, that the coordination number of lanthanides is always higher than in transition metals. So you typically aim at 8 or 9 donor ligand or donor atoms around the lanthanides, and it's difficult. Well, what you could do is, I think, maybe making the ligand or the part of the linker that coordinates to the lanthanide rather bulky. Because that also in simple coordination chemistry is often a way to reduce the coordination number. If you really have a bulky substituent, then you prevent small molecules, for instance, to also coordinate to the lanthanide. And I think if you could translate that to MOF synthesis, that could maybe also work to prevent these small molecules to coordinate to the lanthanide. I think that might be an option. Yeah, but it can be synthetically rather challenging, of course. Yeah,
Yes,
the case. Yeah,
I'm agree. Yeah. Okay, Rick. Thank you so much again for your presentation.
Thank you. It was really my pleasure.
Yes, and we continue with the future collaboration, right?
Sure. Yeah, absolutely.
Okay. Thank you, Rick.
Yeah.
See you.
See you. Bye.
Bye. Alberto.
Thank you, Rick, for your
Te cedo la
presentation.
palabra.
Gracias, Germán. Ahora vamos a seguir con la charla de Felipe Gándara, que es actualmente investigador del Instituto de Ciencias de Materiales de Madrid